Have you ever wondered how does memory work? Memory is a complex cognitive process that enables us to store, retain, and retrieve information and experiences. It plays a fundamental role in our daily lives and is crucial for learning, decision-making, and understanding the world around us. How are we then able to process these complex information? We are able to process information because we have brain. Processing information in the brain relies on remarkable capabilities of neurons, which is the fundamental building blocks of the nervous system. Neurons are specialized cells that communicate with each other through electrical and chemical signals. Here's an overview of how this process works. The process begins when an action potential, an electrical signal, travels along the length of a neuron's axon. Action potentials are triggered when the neuron receives a stimulus that exceeds a certain threshold. This electrical signal carries information and is used to communicate between neurons. The action potential travels down the axon, eventually reaching the end of the neuron's axon, known as the axon terminal or presynaptic terminal. Inside the axon terminal, there are tiny sacs called synaptic vesicles. These vesicles contain neurotransmitters, which are specific chemical messengers that transmit information from one neuron to another. Different neurons use different neurotransmitters. When the action potential reaches the axon terminal, it triggers the opening of voltage-gated calcium channels, calcium ions, into the axon terminal, leading to the fusion of synaptic vesicles with the neuron cell membrane. This fusion causes the synaptic vesicles to release their neurotransmitters into the synapse. Neurotransmitters are released into the synapse, which is the small gap between the presynaptic neuron, the one sending the signal, and the postsynaptic neuron, the one receiving the signal. These neurotransmitters diffuse across the synapse. On the postsynaptic neuron's membrane, there are receptor sites specifically designed to recognize and bind with certain neurotransmitters. This binding is highly selective, as different neurotransmitters fit into their corresponding receptors, like a key in a lock. The binding of neurotransmitters to their receptors on the postsynaptic neuron can have two main effects. If the neurotransmitter-receptor interaction is excitatory, it can lead to the depolarization of the postsynaptic neuron's membrane, making it more likely to generate an action potential. If the interaction is inhibitory, it can lead to hyperpolarization, making it less likely for the postsynaptic neuron to generate an action potential. The effect of neurotransmitters on the postsynaptic neuron, either excitation or inhibition, depends on the specific receptors and the type of neurotransmitter released. The postsynaptic neuron integrates the information from multiple synapses to determine whether it should generate its own action potential, continuing the transmission of the signal.
Have you ever stopped to ponder how a simple thought, like the taste of your favorite dessert or the melody of a catchy song, is stored in your brain? It's a fascinating journey, and it all starts with a tiny cell, the neuron. Every human brain is a bustling city of around 100 billion neurons. These neurons are the unsung heroes behind every memory, every thought, and every emotion you've ever experienced. Imagine neurons as the brain's communication system, passing messages between different areas of the brain and from the brain to the rest of the body. But how does a neuron store a memory? Let's delve into this fascinating process. Think of the brain not just as a collection of neurons, but as a network of connections. These connections, known as synapses, are where the magic of memory formation happens. Each neuron in your brain can connect to tens of thousands of other neurons, forming a complex web of communication. When you learn something new or have a new experience, these connections change. This change, known as synaptic plasticity, is the foundational process for memory and learning. So imagine you're trying a new dessert for the first time. As you taste the sweet, creamy flavor, your brain is busy at work. The neurons involved in taste and pleasure fire up, and the synapses between them strengthen. The next time you taste that dessert, those same synapses fire up again and the memory of that delicious flavor comes flooding back. This process of synaptic change is not a one-time affair. It's a constant, dynamic process. Every new experience, every piece of information learned, every emotion felt, alters the synaptic connections in your brain. This constant reshaping and reorganizing is what makes your brain incredibly adaptable and your memory astonishingly vast and diverse. So to summarize, memory is not a static entity stored in a particular corner of your brain. It's a dynamic process that involves the continual change and strengthening of synaptic connections between neurons. It's how your brain encodes, stores, and retrieves information. Every memory you have is a testament to your brain's remarkable ability to change and adapt. That favorite dessert of yours? It's not just a tasty treat, it's a symphony of synaptic changes in your brain. The catchy song you can't get out of your head? It's a melody etched into the synapses of your neurons. So next time you recall a cherished memory or learn something new, pause for a moment to appreciate the astounding complexity and adaptability of your brain. After all, the brain's ability to change and adapt to form and recall memories is what makes you, you. It's a fascinating journey, isn't it? Have you ever pondered about how a computer can identify a cat from a dog, or how your smartphone understands your voice commands? Well, the answer lies in the fascinating realm of artificial intelligence and neural networks. Imagine the human brain. It's a complex mesh of billions of neurons, each interconnected, forming an intricate web that facilitates thought, understanding, and decision-making. Now picture a computer system designed to mimic this complexity. That, in essence, is a neural network. A neural network is a series of algorithms that endeavors to recognize underlying relationships in a set of data through a process that mimics the way the human brain operates. It's like teaching a computer to think and learn. The neurons in this network are layers of mathematical functions, each feeding into the next, and they can adapt and change as they are exposed to more and more data. On the other hand, artificial intelligence, often referred to as AI, is a broader concept. It's the science of making machines perform tasks that would require human intelligence. This includes learning, reasoning, problem-solving, perception, and even language translation. AI operates on the principle that a machine can exhibit traits of human intelligence. So how does a neural network fit into AI? Well, think of neural networks as the engine under the hood of the shiny AI car. Neural networks provide the computational might, allowing AI to sift through vast amounts of data, identifying patterns, and learning from them, much like a human brain would. Now, the fascinating part about neural networks is their ability to learn. They can improve their performance as they process more data. This learning process is called training. During training, the network learns to adjust its weights and biases in response to the errors it makes, thereby improving its performance over time. However, it's crucial to understand that while neural networks and AI are remarkable technologies, they are not without limitations. For instance, they require vast amounts of data to learn effectively and can sometimes arrive at incorrect conclusions. In sum, a neural network is a computational model based on the human brain that helps machines to learn and make decisions. Artificial intelligence is a broader concept that encompasses neural networks and other techniques to enable machines to emulate human intelligence. Both concepts are integral to the development of intelligent machines, but they also have their own sets of challenges and limitations. As we venture further into the age of technology, the importance and influence of neural networks and AI will only continue to grow, shaping the world around us in ways we can only begin to imagine. The future, it seems, is not just human but also artificial.